Welcome to Not Your Dad's Math. I'm Mike, and today we'll be creating a video input delay meter on an FPGA. The heart of this project is a photodiode. We'll be using an Everlight PD204-6C. We'll reverse bias the diode and convert its current to a voltage through a resistor. The TV that we'll be testing produces about 80 nanoamps of current through the photodiode. To overcome the input offset voltage of the op-amp, we'll use a resistor size of 100 kiloohms. Coupled with the capacitance of the photodiode, we'll get a response time of about a microsecond. We'll amplify the signal with a low-voltage CMOS rail-to-rail op-amp from Microchip. In a non-inverting configuration, we'll amplify a 5 mV signal up to half of the supply voltage from the FPGA board. This means we'll need a gain of about 330. Our circuit will also include a trim pot to attenuate the gain by a factor of 10. This will allow us to use the same circuit to test brighter video sources. By calculating the gain in decibels, we can estimate the amplifier's bandwidth from its datasheet. At maximum gain, we can expect this amplifier to give us a response time better than 12.5 microseconds. In the next stage, we'll convert the analog signal from the photodiode into a digital signal using a low-voltage CMOS push-pull comparator, also from Microchip. The comparator's reference voltage will be configurable with a trim pot. The comparator will also be configured with about 100 mV of hysteresis. This will prevent any extraneous switching in the digital signal from noise amplified in the first stage. By using the hysteresis formulas for this non-inverting circuit, we can calculate the required resistor values. Finally, we can draw the complete circuit design. Don't forget to add bypass capacitors to the supply voltage pins of both integrated circuits. 100 nanofarad caps should suffice. Now, we're ready to go build the prototype. We'll start by soldering a ribbon cable to our prototype board. The other end of the cable has a JST-XH connector attached. This will let us easily connect to a PMOD breakout board attached to the FPGA. Next, we'll solder in all of the resistors. Then we'll solder in the comparator. And then the op-amp. Next, we'll solder the 100 nanofarad bypass capacitors. Then we'll solder both trim pots. We'll solder in a 1 microfarad electrolytic capacitor across the supply rails. And finally, we'll add the photodiode, making sure it sticks out high above the other components. Now we'll add jumper wires to route the signal across the board. We'll do the same for the source voltage, and also for ground. Finally, we'll make solder bridges to complete all of the connections on the back side of the board. Take your time and make sure to complete all of the connections in the circuit. Check your handiwork for any shorts or missing connections. Now we're ready to read this sensor from our FPGA. We'll start by creating a Vivado project for our Nexys A7-100T board. Next, we'll set up constraints to name our clock and LED ports. This lets us control the names we use to access these ports from our top-level module. Now we can create a top-level module called Video Delay. It wires in the ports that we named in our constraints file. We'll assume the existence of a light sensor module. It will output an on signal when the sensor detects light. We'll turn on all of the LEDs when the sensor is on. The light sensor module will use a special register to synchronize the signal with the system clock. This ensures we won't propagate a metastable flip-flop output to other parts of the circuit. We'll wrap up by wiring a port name to the sensor and running a build. After copying the bitstream file to a USB stick, we're ready to try it out. Here you can see that the LEDs light up when white letters scroll past the photodiode. Next, we'll move on to driving a DVI signal. We'll start by wiring in port names for our DVI PMOD from 1-bit squared. Then we'll wire these ports to a DVI Driver module that we'll be creating soon. Our driver will require a pixel clock running at 74.25 MHz. We'll create this using the Clocking Wizard IP from Xilinx. We'll also need to create a second clock with a phase offset from the pixel clock. This will be used to achieve the setup and hold times for the DVI outputs. The required phase offset of 125 degrees was determined by experimentation with another circuit. After wiring in both clocks, we're now ready to build the DVI driver circuit. All of the output pins will be driven by specialized DDR circuits. These are available in all of Xilinx's 7 series FPGAs. We'll instantiate each DDR output from a Vivado code template. The data outputs will drive the lower 12 bits on a rising clock edge and the upper 12 bits on a falling clock edge. The other outputs for H-Sync, V-Sync, and Data Enable will output the same value on both clock edges. By driving all of these signals as DDR outputs, we can avoid the need for complex output timing constraints. After wiring up flip-flops to feed the DDR outputs, we'll work on building the DVI driver state machine. As the DVI driver advances through each line of pixel output, it cycles through 4 states: the back porch, the active region, the front porch, and the sink. Each horizontal line cycles through a similar set of states. Pixel data is output when both the vertical and horizontal states are active. Our circuit will cycle through these states by counting the appropriate number of pixels or lines. You can see that this is where our 1280 by 720 resolution comes from. In fact, if you multiply all horizontal counts by all vertical counts by 60, you'll arrive at 74.25 million, our pixel clock frequency. Once we've set up our state machine cycling logic, we can drive all of the output flip-flops from the current state values. Using the horizontal states counter, we can output a gradient of colors across the screen. Here's the output on our testing TV screen. Next, we'll develop some tools for building a user interface. As a first step, we'll wire in all of the ports for our 7-segment displays. Next, we'll create a module called Sevens that takes care of refreshing all of the 7-segment display outputs. All 8 digits of the display will be updated at a rate of 1000 Hz. To achieve this, we'll cycle through lighting up 1 digit at a time every 12,500 clock ticks. The anode signals determine which digit is turned on, and the cathode signals determine which segments are lit. All of these signals use inverted logic, so we'll perform the inversions here. This makes the module's interface a little easier to use. Once we've wired the Sevens module to the top level, we'll create a new module for translating decimal numbers to segment signals. By referring to a numbering diagram for the 7 segments, we can determine which bits to turn on for each decimal digit. Next, we'll create a Sevens demo module. It will let us increment or decrement a decimal value for each of the 7-segment digits. The up and down buttons will handle incrementing and decrementing, and the left and right buttons will handle selecting a digit for editing. After wiring in the Sevens demo, we'll have to handle debouncing all of the button signals. Push buttons typically generate a rapid sequence of rising edges as the button vibrates while making electrical contact. We'll create a debouncer module that converts this noisy signal into a single rising pulse. Our debouncer module will have 2 parameter options. One controls whether we hold the output signal high while the input signal is high. The other controls how many clock ticks to perform debouncing. The debouncer will alternate between 2 states. In the ready state, we wait for a change in the input signal. Upon change, we immediately update the output signal and transition to the debouncing state. In the debouncing state, we count up to the debouncing period and then switch back to the ready state. After wiring in our button ports to the top level, we'll be ready to test. So here I'll show a couple of increments and then speed up the video to click around really fast. Next up, we'll build a pattern generator for our DVI driver. We'll start by assuming that we have a pattern selector module that lets us choose amongst the 9 patterns using the buttons. We'll also create a reusable synchronizer module so that we can synchronize the button presses before we debounce them. Now we can synchronize our button signals at the top level and pass them into our pattern selector. The pattern selector module keeps track of which pattern is currently selected and outputs the current pattern value as a number between 0 and 8. It debounces the button signals and wires up handlers for moving the pattern around the screen. Next, we'll update the DVI Driver module to output a 5x5 pixel pattern. Its position on the screen will depend on the currently selected pattern number. The driver will take about 100 microseconds to render the pattern from top to bottom. If we hold the photodiode in the center of the pattern, our measurement should be accurate to within plus or minus 50 microseconds. Rendering is simplified by calculating whether the horizontal and vertical counts are within range for the currently selected pattern. A white pixel is sent to the output whenever both counts are in range. Next, we'll create a specialized segment driver for showing the currently selected pattern on the 7-segment display. After handling synchronization issues and setting up a false path between the system clock and pixel clock domains, we'll be ready to test. Here you can see that button presses move the 5x5 pixel pattern around the screen. You can also see how the photodiode sensor correctly detects the pixel pattern. Next, we'll build the timer module. We'll need to make 2 modifications to our DVI driver. The first will allow the timer module to enable or disable the output. The second will make the driver output a signal when the center pixel of the pattern is rendered. The timer module will perform 3 main tasks in a loop. First, it will enable the DVI output. Next, it will start timing a measurement when the DVI driver outputs the center pixel. Last, it will stop timing the measurement when the photodiode sensor turns on. After updating the 7-segment display with the latest measurement, the timer will disable the DVI output and pause for a brief delay. The timer's loop is managed with a simple state machine, and measurements are stored in a 4-digit binary-coded decimal counter. The counter increments every 100 microseconds and stops counting at 999.9 milliseconds. The counter's value is then used to directly drive 4 7-segment display digits. After cleaning up a few more clock domain crossing issues, we're ready to test the final circuit. We'll start with a measurement of the top left pixel pattern. I found that the photodiode is really sensitive to being held still and at the right angle. With a little effort in holding still, I was able to get a stable reading of 48.8 milliseconds. Next, we'll move to the top center pattern. Here I got a stable reading of 47.7 milliseconds. Now we'll switch to the top right pattern. In 720p, each line takes about 20 microseconds to render, so we don't really expect any variability between the top 3 pixel patterns. However, there is some difference in the brightness of the backlight between these 3 positions. So we'll use the fastest measurement as the official measurement for this row. Here we get a stable measurement of 47.0 milliseconds, so we'll take that as our top row measurement. As we move on to the second row, it's important to think about exactly what it is that we're measuring. In addition to any margin of error delays and any possible output delay from the DVI chip, we're measuring the TV's input delay for any buffering or processing that it performs. But very importantly, we're also measuring the pixel response time. That's the amount of time it takes the LCD pixel apertures to open up and let the backlight through. Since our sensor circuit is tuned to only detect the fully brightened backlight, our pixels must transition from fully closed to almost fully open before our sensor can detect them. For older and cheaper screens, this can take time on the order of tens of milliseconds. The best stable time that I saw for the middle row was 37.0 milliseconds. The final thing that we can measure is the refresh period of the entire screen. Once the TV finishes buffering and processing the input signal, it has to update all the pixels on the screen from top to bottom. We can calculate that 15.9 milliseconds will elapse between our DVI driver rendering the top and bottom rows. The difference in time that we measure between the top and bottom rows will include the full screen pixel refresh. The best stable measurement of the bottom row comes out to 26.7 milliseconds. So the top row measurement minus the bottom row measurement minus 15.9 comes out to 4.4 plus or minus 0.2 milliseconds. This TV is capable of a 240 Hz refresh rate, which would require a minimum 4.2 milliseconds pixel refresh. It's interesting that our measurement is in agreement with this. As for gaming at 60 Hz, all I can say for sure is that this TV is delayed by 1 to 3 frames, depending on how strictly you define a delay. Thanks for watching. I'm Mike, and this has been Not Your Dad's Math.
That I can only make his drum sound like this. I saw you off tonight. That's enough for my voice.